Okay, hello and welcome back. In this video, we're covering section 9.5. So we're continuing our discussion on vectors, and we'll look at an operation called the dot product. So we'll find out what that is, the dot product between two vectors. This will allow us to find the angle between two vectors. We'll be able to determine if vectors are parallel or perpendicular. We'll also decompose a vector into two orthogonal vectors. So we'll describe what that means as we go through. So let's define this operation called the dot product. So we have two vectors v and w. Let's call v a1 comma b1 and w which is a2 b2. So the dot product is kind of like multiplying them together. We use a dot in between. So v dot w. To get this, we multiply the two horizontal components, so a1 times a2. Then we add that to the vertical components multiplied, b1 times b2. So note that the dot product produces, this will end up reducing to just some value. It produces a scalar and not another vector. When we added and subtracted vectors with each other, we produced another vector, but the dot product produces a scalar, just a value, some number. So we have our textbook definition, v dot w, a1, a2 plus b1, b2. So let's get some practice finding the dot product between some vectors, and we'll see some properties emerge. So we're given vector v as 2, negative 3, or 2i minus 3j, and the vector w is 5, 3, 5i plus 3j. So let's find v dot w. Well, that will be the multiplication of horizontal components, so 2 times 5, plus the multiplication of the vertical components, so negative 3 times positive 3. So that will give us 10 minus 9, or positive 1. We just get some scalar, some number. Part B asks us to find w dot v, so we're just reversing the order here. So we get the same value. So that would be, well, we would just flip this multiplication. It would be 5 times 2 plus 3 times negative 3. So that will still give us 10 minus 9, or positive 1, meaning that the order of the dot product doesn't matter. A technical way to say that is that the dot product is commutative. We can reverse the order. We can say v dot w or w dot v, and we get the same result. Part C asks us to dot v with itself, so we can do v dot v. Well, that would just give us 2 times 2 plus negative 3 times negative 3, or 4 plus 9, which is 13. So we can dot a vector with itself. D asks us for w dot w. So this would be 5 times 5 plus 3 times 3, or 25 plus 9, which is 34. Part E asks for the magnitude of v. So if you recall from last time, we get the magnitude via the Pythagorean theorem. This will be the square root of a squared plus b squared. So that for v, that would be the square root of 2 squared plus negative 3 squared. So that's the square root of 4 plus 9, or the square root of 13. So notice when we dot a vector with itself, we get basically what's underneath the square root. V dot v is 13, where the magnitude of v is the square root of 13. So we could say a vector dotted with itself is equal to the magnitude squared. That could be another relationship. And then f asks for the magnitude of w. So that means we should expect to get the square root of 34. So that would be the square root of 5 squared plus 3 squared, or root 25 plus 9, which, yeah, gives us the square root of 34. So this gives us some properties of the dot product, which the text defines for us here. We said that the property is commutative, or the dot product is commutative, meaning u dot v is equal to v dot u. We didn't see an example of this, but we get a distributive property with the dot product, meaning if we're dotting a vector with the sum of two vectors, the operation will distribute. We can describe that as u dot v plus u dot w. And then we just saw a vector dotted with itself is equal to the square of its magnitude. In this last statement, this is the 0 vector. That just means 0, 0, or 0i plus 0j. So a 0 vector dotted with any vector, if we're doing that. And vector is, we'll call vector v ab. Well, that would be 0 times a plus 0 times b, which is 0. So another property here. So our next section is on finding the angle between two vectors. And we'll see the dot product show up here too. So let's imagine we have some vector v, call this vector v. Actually, let's use u and v, because that's how it will show up in the definition. So we'll call that vector u. We'll call this one vector v. So we want to be able to find the angle between these two. So how can we do that? If we imagine some other vector connecting these two, we can form a triangle. We could call this side of the triangle the magnitude of v. We can call this side of the triangle the magnitude of u. And this other vector, we can actually describe this as u minus v. Vector u minus vector v. If we imagine subtracting v from u, we would place v but in a flipped direction on top of u. So technically we would get, we place v here, we would get this vector, but we can move it to any point in space. We can have an equivalent vector placed on that side to produce our triangle. So that means that side length would be the magnitude of u minus the magnitude of v. Just to jump to the formula so we can see it first, they'll tell us that the cosine of the angle between vectors is equal to u dot v divided by the magnitude of u times the magnitude of v. So if you're comfortable just memorizing this and working with it, we could plug all of this in, find these attributes, and then take the inverse cosine in order to find our angle. But if you're curious where this formula comes from, we can actually get it via the law of cosines. Having this triangle where we can describe the three side lengths and we want to find this inner angle. So if you recall, let's view it a little bit differently. If I just called this angle A, so this would be side length A, let's call this angle B, angle C, side length B, side length C. By the law of cosines, we could say a squared equals b squared plus c squared minus 2ab times the cosine of angle A. So we can use this same equation with our triangle where our side lengths are described as the magnitudes of these vectors. So let's find some of these components. Let's define this a little bit more concretely. Let's call u the vector a1, b1. We'll call v the vector a2, b2. So that makes u minus v. Well, that would just be the subtraction of their horizontal components. So a1 minus a2, b1 minus b2. So let's describe their magnitudes. We can say the magnitude of u will be the square root of a1 squared plus b1 squared. The magnitude of v would be the square root of a2 squared plus b2 squared. And then the magnitude of u minus v would be the square root of a1 minus a2 squared plus b1 minus b2 squared. So now that we have our side lengths defined, let's use this law of cosine statement. So copying this formula, our a squared would be the magnitude of u minus v squared. So say by the law of cosines, the magnitude of u minus v squared should equal the sum of the squares of the other two sides. So we can say u magnitude of u squared plus the magnitude of v squared. And we have our minus 2ab cosine a. So minus 2 times the magnitude of u times the magnitude of v times the cosine of theta. And that's the angle between the two vectors. So let's plug everything in that we have and see how things will simplify. Well, first, maybe I'll rearrange this a little bit. Let's move this term over to the left because we ultimately want the cosine on the left to describe it as the formula is given up here. So I'll add that term to the other side. So I'll get positive 2 times the magnitude of u times the magnitude of v times the cosine of theta. And then let's subtract this squared term over to the right side. So this should equal magnitude of u squared plus magnitude of v squared minus the magnitude of u minus v squared. So now let's plug in all of our components. I'm going to leave this magnitude of u times the magnitude of v on its own, because I see that that will show up on the right side. We'll eventually divide that over. So let's just plug into the right side everything that we have. That means that 2 times the magnitude of u times the magnitude of v times the cosine of theta would equal, well, the magnitude of u squared, that should just be a1 squared plus b1 squared. We'll lose the square root. The magnitude of v squared would be a2 squared plus b2 squared minus the magnitude of u minus v squared, so we'll lose the square root there. We'll have to subtract everything. And I'm going to go ahead and FOIL out these two expressions. So a1 minus a2 squared, that should give us a1 squared minus 2a1 times a2 plus a2 squared. Then we have plus our second factor squared. So that should give us b1 squared minus 2b1 times b2 plus b2 squared. So it's looking pretty messy, but notice everything that's going to cancel here. We have a1 squared minus a1 squared, so those will cancel out. We would have b1 squared minus b1 squared after distributing that negative in. Then we have a2 squared, we'll get minus a2 squared, b2 squared minus b2 squared. So all that will be left inside this bracket is the minus 2a1a2 minus 2b1b2, and this negative will distribute, so it will make them both positive. So let's write our simplified expression. So I have 2 times the absolute value, not the absolute value, sorry, 2 times the magnitude of u times the magnitude of v times the cosine of theta should just be equal to 2a1a2 plus 2b1b2. So then, solving for the cosine, I would divide the 2 magnitude of u magnitude of v over to the other side. So we'll get a fraction. We can factor a 2 out of that, what will be on the top, since they both have a 2. So 2 times a1, a2 plus b1, b2. This will be over 2 times the magnitude of u times the magnitude of v. So notice our 2's will cancel, and then a1, a2 plus b1, b2, that was how we defined the dot product between u and v. So that means we can ultimately say the cosine of theta equals u dot v over magnitude of u times the magnitude of v. So you definitely don't have to memorize all of that, but just wanted to show how we could derive this formula for the angle between two vectors. Technically it's for the cosine of the angle between the two vectors. Then we can take the inverse cosine of both sides. So we can describe it as the dot product between our two vectors divided by the product of their magnitudes. So it's also wanted to use this as an example of the law of cosine showing up again. We saw that in a previous section, so it's cool to see it used here in the derivation of a new formula that we can use. So let's practice using this after we've kind of proved to ourselves why its structure makes sense. So we're given two vectors. Our vector u is 4, negative 3, or 4 minus 3, 4i minus 3j. And then our vector v is 2 comma 5. So if we're saying the angle between these two vectors, or the cosine of the angle, is u dot v over magnitude of u times the magnitude of v. Let's find out each of these components. So u dot v should be 4 times 2 plus negative 3 times 5, or 8 minus 15, which is negative 7. Then let's find the magnitude of u. That would be the square root of 4 squared plus negative 3 squared. That looks like the square root of 16 plus 9, or root 25, which will give us 5. And then let's find the magnitude of v. So that will be the square root of 2 squared plus 5 squared, or the square root of 4 plus 25, or root 29. We'll have to leave that one under the square root. So that means we can say the cosine of our angle is equal to the dot product, which was equal to negative 7, over magnitude of u, which is 5, times the magnitude of v, which is root 29. So that means our angle should be the inverse cosine of this value, which if you plug that in, and if you're in degree mode, you should get about 105 degrees. So if you're asked to find the angle between vectors, we'll use this formula. So we need to first find the dot product and then their magnitudes. So we plug that in. Oops. We plug that in here, and then take the inverse cosine of our result, and that will give us our angle. Jump to a different section here. Okay, so we could also determine whether our vectors are parallel or perpendicular using a couple different methods. First, we'll see if vectors are parallel. If our vectors are parallel, so let's imagine some vector v. You can say w is over here. Maybe they have different magnitudes. We can move them anywhere in space. So if they're parallel, that means they have the same directional angle. So in one sense, we could say the angle between them is 0. That would be one way to determine if the vectors are parallel. But if we place them on top of each other, if we move them around, they have the same direction, so that means one is really just like a scaled version of the other. We could say that our vector w is some scaled version of v. So we can say vectors are parallel if we can say some vector w is c times some vector v. So some scaled version, a scalar multiple, that would be the technical term. Or another way to test to see would be to show that the angle between them is 0. So example 3, it's already worked out, but let's look at these two vectors to see that they are parallel. So we're given vector v as 3, comma, negative 1, and w is 6, comma, negative 2. So we should see, well, if we pulled out a 2 from vector w, we would get 3, negative 1, which is our vector v. We can say w equals 2 times vector v. That alone is enough evidence to show that they are parallel to each other. W is a scalar multiple of v. But we could also use the angle between them, and so that's what they have worked out here as well. So v dot w gives us 18 plus 2, which is 20, over magnitude of v times the magnitude of w. They've worked out the magnitudes as root 10 and root 40. So this ultimately gives us an expression that reduces down to positive 1. So we're saying the cosine of the angle is equal to 1. If you took the inverse cosine, you should get 0, or just looking at that, the angle that produces a cosine of positive 1 is the angle 0. So if we get an angle of 0, or if we get that one vector can be described as a scalar multiple of the other, we can say that the two vectors are parallel. So how about if they are perpendicular? Well, the term that we use for vectors is that they are orthogonal. It means that they meet at a right angle. Meaning that the angle between vectors is 90 degrees or pi over 2 radians. So how can we determine that without even doing our whole angle calculation? Well, let's recall the formula for the angle of two vectors. The cosine of theta is u dot v over magnitude of u times the magnitude of v. Well, if our angle is 90 degrees, then the cosine of 90 degrees is 0. So that means 0 would equal u dot v divided by their magnitudes. Which means we can multiply this over, it would still be 0. So we get this expression that if the vectors are orthogonal, then their dot product is equal to 0. We can say u dot v would be equal to 0. So that's a way to tell if two vectors meet at a right angle. If we take their dot product and we get a 0 value, then they are orthogonal. That's what they give us here. Orthogonal if and only if they use v and w here, if v dot w is equal to 0. So example 4 gives us two vectors. We have vector v as 2, negative 1, and vector w is 3, comma 6. So let's find their dot product. V dot w would be 2 times 3 plus negative 1 times 6, or 6 minus 6, which is 0. So therefore we can say v and w are orthogonal. angle between them, however they're oriented, will be 90 degrees. All right, our last piece of this section is decomposing a vector into two orthogonal vectors. So here's what we mean by that. If we have some vector v, and let's say we have some other vector w, we might be asked to decompose this vector v into the sum of two vectors where one vector is parallel to some other given vector. We can call this v1. It's parallel to w, and we'll call this v2. This is another vector that is perpendicular to the vector w. I drew w flat like this because it makes it a bit easier to visualize, but it doesn't necessarily have to be a straight horizontal vector. This can have any particular orientation. So it's not just the I and j form of the vector. We're relating this to some other vector. We're parallel and perpendicular. Our components will be parallel and perpendicular to some other given vector. So this will still be our magnitude of v. We can describe this as the angle, not necessarily the direction of our vector v, but the angle between the two vectors. This v1 vector, it has a particular name. You can almost imagine that this vector v is like dropping a shadow onto vector w. We call this the projection of v onto w. And then the second vector v2, you can use a similar argument when we were building that triangle in defining the angle between vectors. You can describe this as vector v minus v1. If we took our vector v, subtract v1, meaning it would go in the other direction, the result would be this vector, which is equivalent to the one over here. So we want to be able to describe this vector v1, which we could see as just a scaled version of vector w. If we scale it down to just this horizontal component here, we want to scale down the magnitude, we would get our vector v1. And just looking ahead, we have this kind of messy description. We see it'll be ultimately described as v dot w divided by the magnitude of w squared times the vector w. So that is some scalar applied to the vector w. We're scaling it down. But I just want to show where this formula will come from. So you can imagine the cosine of this angle. This is the angle between the two vectors. But just looking at this as a triangle, it would be the adjacent side length, which we can describe as the magnitude of v1, divided by the hypotenuse of the triangle, which is the magnitude of v. But we also know that the cosine of the angle between two vectors is the dot product of the two, so v dot w divided by the magnitude of v times the magnitude of w. So these two things must be equivalent to each other. So that means if we multiply this magnitude of v on the left side up to the right side, it will cancel with the 1 in the denominator. So we get this statement that the magnitude of v1 is equal to v dot w over just the magnitude of w. So this is useful for us to know this magnitude because if we want to scale this vector w, well, we could first reduce it to the unit vector in the direction of w. We could reduce its magnitude to just 1, and then multiply it by the magnitude of v1, and that would give us the vector v1. So meaning we can describe our vector v1 if we first find the unit vector in the direction of w, well, that would be the vector w times 1 over its magnitude. So that's scaling its magnitude down to 1, and then we can multiply this by the magnitude of v1. So that will produce the right scale for magnitude. So we would multiply by this term. So I can say this would be, let me write this a little bit nicer. So we have our magnitude of v1, v dot w over magnitude of w. Then our unit vector in the direction of w, which is 1 over magnitude of w times the vector w. This is what's going to give us our magnitude squared in the denominator here. So we can say v1, the vector v1, or the projection of v onto w, will be v dot w over the magnitude of w squared times the vector w. So it's a scaled version. All of this will produce some scalar, which will produce, when multiplied by w, produce the vector here. So again, don't need to memorize this whole process. But since these formulas are kind of hard to read intuitively just by looking at them, it's helpful to see how they can be produced. So we have our theorem for the vector projection of v onto w. This is the formula we just derived. V dot w over magnitude of w squared times w. So the decomposition of our vector into two vectors where one is parallel to w, one is perpendicular. Our first vector is what we just found, the projection. And then the second vector we get just by subtracting our first vector that we found from v. Because we had said earlier that this vector is described as v minus v1. So let's see an actual problem. Let's put it into practice. So we're given a vector v as I plus 3j, so I can describe that as 1, 3. And vector w is I plus j, so 1, 1. So first it asks us to find the vector projection of v onto w. So that's our v1. We said that should be v dot w over magnitude of w squared times the vector w. So let's find the dot product and then the magnitude of w. V dot w should be 1 times 1 plus 3 times 1, or 1 plus 3, which will give us 4. And then the magnitude of w squared would be the square root of 1 squared plus 1 squared, or the square root of 2, and then we'll square that. So we should just get 2. So that means our vector v1, or the projection of v onto w, is v dot w, which is 4, over magnitude of w squared, which is 2, times the vector w, which is 1, 1. So that will become a 2 on the outside, which will distribute in. So we get 2, 2, or 2i plus 2j. And then it asks us to decompose vector v into two vectors v1 and v2, where v1 is parallel to w and v2 is orthogonal to w. v1 we just found already. That was the projection. So we said we can find v2 by finding v minus v1. So that would be 1, 3 minus 2, 2. 1 minus 2 is negative 1, 3 minus 2 is positive 1, so negative 1, 1. That will be our v2. So that means our two orthogonal vectors would be 2, 2 for v1 and negative 1, 1 for v2. So if we're asked this kind of question, decompose a vector into two vectors where our first vector is parallel to some other vector and our second is orthogonal to some other vector. We find v1 using this projection formula. And then we find v2 by subtracting v1 from v. Alright, that'll be it for this section. So we defined the dot product between two vectors. We found the angle between two vectors. We saw techniques for determining whether vectors are parallel or orthogonal, and then how to decompose a vector into two orthogonal vectors. There's some additional physics-based questions involving computing work at the end of this section, so that's worth checking out to see how these kind of this kind of work could be applied to more physics-based questions. Alright, that will be it for today, and I'll see you next time.